Conducting electricity with zero resistance is not the only incredible property of superconductors. Superconductors are more than just perfect conductors. They are also perfect diamagnets. What does that mean? We call a material diamagnetic when it opposes any magnetic field that tries to penetrate into its core. Water, graphite, and diamond all show examples of diamagnetic behavior, slightly pushing away magnetic fields. A perfect conductor with zero resistance, or resistivity, which is just another measure of electric resistance, can also push away magnetic fields. But this depends on when we apply them. Mathematically, this repulsion of magnetic fields is a consequence of two physical laws working together. Faraday's law, that describes how magnetic fields respond to changes in electric fields, and Ohm's law, that describes how currents flow in conductors. These two laws imply that the magnetic field in the core of a perfect conductor is always constant. To show what this means in practice, we can conduct two different experiments. In a first zero-field cooling experiment, we take a sample of a perfect conductor and we cool it down below its critical temperature without any magnetic field. Now the sample has zero resistivity and its magnetic field must remain constant. If the sample had zero magnetic field inside before cooling, it will keep zero magnetic field after cooling. If we turn on the magnetic field now, it will be pushed out of the core. This is because the perfect conductor does not allow a change in the magnetic field in its interior. The behavior is different in a field cooling experiment. Here, we start with a sample already placed in a magnetic field, and then we cool it. This time, the magnetic field will not be expelled. This is again to avoid any change in the magnetic field in the core of the sample. If we now remove the external magnetic field while the sample is still cooled, it will become magnetized to maintain the same magnetic field in its core. Applying the same two kinds of experiments to a superconductor reveals that it does not behave simply as a perfect conductor. This is because, as we said before, the superconductor is also a perfect diamagnet. That means that the magnetic field in its core must not remain simply constant, but it must be strictly zero. If we performed the zero-field cooling experiment with a superconductor, we would obtain the same behavior as a perfect conductor. The field cannot penetrate the sample when it is cooled below the critical temperature. On the other hand, if we conduct a field cooling experiment, we would see that the magnetic field is spontaneously expelled from the core. When we remove the magnetic field, we obtain the same final state as in the zero-field cooling experiment. This finding is very important. Its final state does not depend on which path we choose to get there. This tells us that just like the liquid or solid phase of a material, superconductivity is the thermodynamic phase of matter. This means that superconducting phases can exist across different materials and possess certain distinguishing properties which do not rely on microscopic details.